you very much. I'm very happy to be here to give this talk. Actually, that's my first time to talk about this. The reason that I select this topic is that I try to find something that connects with the WINLAB. And I'm working a lot on the optical communication and the networks, which are wired part. And now the wired and wireless cannot be really separated, like computing and communication cannot really separate it. We need to think everything to have an optimized solution for the overall world. This is the outline for my talk, and yeah, I guess many of you are not that familiar with my university and also the country, so I would like to spend some slides to promote the country and the university. And the second big part is the main topic for today, that I want to show our recent research activities on the 5G transport networks, and also something related to the background. And also I want to try to connect our research activities to the wireless part and see that if we have chance to have more collaborations and also maybe some discussions and brainstorm for something, for big idea. And then this is the KTH, and all the numbers are like KTH required faculties to promote in the worldwide. And that's not that important, but anyway, Sweden is not that big countries, and we have two top technical university. One is KTH, Royal Institute of Technology. KTH is a Swedish abbreviation for Royal Institute of Technology. And another one is the one that I will move very soon in April this year, actually. Chalmers University of Technology. KTH is in Stockholm. Chalmers in Göteborg. Göteborg is the second largest city in Sweden. Stockholm is capital. And both of them have very similar world ranking. And the engineering school for particularly electrical engineering are pretty good in these two universities. And in Sweden, 1/3 of engineers are produced by KTH, another third produced by Chalmers, and the last third are produced by the other universities. Okay, and also about Stockholm. Stockholm is a very beautiful city, so very welcome to visit. And it's not like Italy or France that are famous, but that give you different styles. And the downtown of Stockholm is made by many islands. This one is the center one, the biggest one, where the palace. Sweden is a kingdom country, so the palace is in this one. It's called Gamla stan in Swedish. In English, that means old town. And as Stockholm is not enough, so we have very long darkness now and very long daytime in the summer as a compensation. And this picture was taken in the summer. You see that that's not really dark in the midnight. You see the city is beautiful under the moon and with the lights. And the city hall is the symbol of Stockholm. Every year this Nobel stuff happened here. And I will also spend one more slide for City Hall. As we are the Zoya Institute of Technology, we have many events also organized here, very elegant. And this is a palace, and this is Summer Palace, where the royal family stay every day. And also City Hall. And there are two big halls inside the City Hall. One is Blue Hall. This one is Blue Hall, which is not really in blue, but named as a Blue Hall. And the other one called Golden Hall. The Golden Hall is really golden, and that's decorated by the real gold. And these two pictures were made for the graduation ceremony for KTH, which are very nice one. And I did my PhD at KTH, so I have a chance for this graduation. And several years later, my student also graduated. I was also invited. That's really very nice. And all of you are PhD students, or some of our masters? Most of them. I say it's pity. If you want a second PhD, it's very motivated to be there. Really nice. Different styles for the ceremony. If you master, you have chance to.
Yes, there are a couple of master students.
And also this is a campus. There are several campuses like Radulus, but not that many. We have maybe two. One is in the downtown, this one is in the downtown. We have everything kind of old style, European style. And also, another campus called the Kista Campus. Kista, in English you may pronounce as Kista, but in Swedish that's Kista. Kista Campus is like, Kista is a place as an ICT clustering in Stockholm. So many ICT companies are kind of located here. The headquarters of Ericsson is here, very close to us. And for my school, now I'm in the School of Electrical Engineering and Computer Science. We are located in Kista Campus. The reason to be there is close to the industry, which trigger a lot of collaborations. And now for the ICT areas, actually the research becomes more and more applied. That's very important to talk with industry guys. And this is a building for us, for KTH, and we are in the optical networks labs. Same as a WINLAB, we have several faculties, and each of us have our own small group. We're not as a size as you are. I guess you are pretty big.
20
faculties, okay. We are not that big. We are 3 faculties, and this picture was taken from summer this year. And for the talk that I talk about, that's more related to our my research direction of 5G transport. Yeah, Lu, my PhD student Lu, Jun, and Xiaoman are mainly working on these directions. And I list some statistics for Radix and KTH. I don't want to compare these two university, but just to give you the general impression about the KTH. Both of ours are older university. Radix, I think 50 years older than KTH. The Radix data I kind of found from Wikipedia. You can correct me.
That's correct.
Okay. The KTH one is from the KTH statistics, so I'm pretty sure that's reliable data.
Yeah, we have about 70,000 students.
And we have much less students because that's a technical university that not cover all the subjects. And from the faculty point of view, I don't know this number is for faculty or more like academic
it's really 12, but maybe I'm wrong.
Okay. Well, for 600, which I list for KTH is about professors, faculty members, associate assistant, and also full professor there. And so that's like our size are like 1/5 of Radix. And we are also public university. Another one, Chinese, that I will move to. That's private.
Oh, it's private?
But in Sweden, private and public, there will be no difference from the faculty side or student side. Yeah, all the students don't need to pay the tuition. It's free for education if you are European citizen. And if you are not, for the PhD education, there are also no tuition fee. And actually, PhD is employed, and you have the benefits, all the benefits for the social, like very famous parental leave in Sweden. It's quite a unique country. So if you are there, you will really enjoy the country. Okay, and here I will talk about the research vision that we are working on for all the areas that I cover. We believe this ubiquitous access for ultra-high bandwidth. And you can see that here cover for our research that cover both telecommunication and data communication. And now the data communication becomes even more and more important from the fiber point of view. That's like a new research big research opportunities in that part. That's important for the data centers and high performance computing, particularly for Sweden. Sweden is north of Europe. even north of the world. It's a very cold country and very good location to host the data centers. We have this cold environment, so that's also become very strategic research areas in Sweden. And for the telecommunication, Sweden is quite a strong country or pioneer country for this. Reflecting from the industrial point of view, we have Ericsson, which is already 100 years working in this business. And for our level, for my group, we are more focused on this access for the end-to-end connections. That's including, that's considered the converged wired and wireless segment. We're also thinking about new applications in which way that will impact the metro networks and also the core networks. Now there are like a new application comes, smart city, cloud, e-science. The connections become a bit different compared with before from the physical layer to the optical layer. There are many things considered like the unicast, the point to point. But once the cloud comes, data centers comes, even distributed data centers comes, this multicast, manicast, anycast will come even in the very lower layer, layer 1, layer 0 for that, not only the higher layer. So when we are doing on the opticals, we also think about in which way to change this architecture to support the new applications. And also for the data centers, we look for the scalable and sustainable solutions. But for the talk today, I mainly focus on this red part, converged wired and wireless segment, and also think about the end-to-end requirement. When you then show me the lab, I'm kind of surprised that you also have many optics and fibers in the lab, and that's kind of the common vision. Yeah, when it comes to this 5G stuff, not only the access part, the radio part need to be optimized. End-to-end is also should come to our mind to think about how to optimize it that way. And for the research interest, as I mentioned, this is two big parts. Core metro access, that's more for telecommunication. Cloud and data center networks, that's more for data communication. And we support two cases, two big application areas, 5G transport networks and also ICT infrastructure for smart cities. Sometimes they are kind of overlapped with each other, not need to be like completely separated. And we also work on different aspects, control and management, energy and cost efficiency, security and reliability. Now security becomes more and more important aspect. Yeah, we work pretty a lot, but not yet 5G transport, but security as core networks. And for my interest, kind of in favor on this cross-layer approach. Cross-layer not only means the network architecture, but also like some push from the application, from the performance matrix. Now some buzzwords like autonomous traffic systems, tackle-tail internet, I guess you are familiar with those terms, remote control, which push actually the performance matrix. We need extremely high reliability, extremely low latency, and at the same time that also push the network architecture design. For the network architecture design, we work for the cross-layer or cross-plane thinking, we work on both control plane and also data plane. And you will see that data plane becomes more and more heterogeneous. Different technology are used there. Even for the wireless, you have Wi-Fi, cellular networks, even the Wi-Fi. I guess you hear about this visible light communications. And also these data centers are integrated with communication infrastructures, metro networks, core networks, different technologies there. And even for the control part, that also could be the hybrid solutions. That could be real radio link or optical links to support control signaling. So the overall network architecture becomes hybrid, and you really need a cross layer. So for my work, we also have like the whole network architecture design, control plane part, working on the service provision, resource allocation, and also we'll work on the transmission issue for like optical communication system, point-to-point link, which I will introduce in my later slides. And now let me come to this main part of my talk, 5G transport networks. When we talk about the 5G transport networks, first we can think about what is 5G. And yeah, I guess you are familiar with 5G or not.
Well, if you can tell us what's 5G, we will gladly hear about it.
Yeah,
Because, you know, everybody claims they know what 5G is, yet nobody can define it. But it's okay.
Yeah, it's a very difficult question. I think you're right. Everyone would like to hear some clear definition of this. It's completely different from the other generation of wireless communication system. Yeah, I don't have definition. I just take this sentence from Wikipedia. 5G is a next generation of cellular mobile network. It succeeds the 4G, 3G, and 2G. Then what you found from the 4G, 3G, 2G, you have some terms that can directly connect them. For 4G, LTE is clear. When you talk about LTE, everyone knows that's 4G. And that's almost equal, what I can say. And for 3G, 2G, the same. Even for the 1G analog systems, that's kind of very clear. But for 5G, when you come to 5G, you cannot find any equal word with this 5G. But we do find some kind of terms that reflect now. Yes, we are talking about 5G. And here I kind of list some terms that I found that have some connections with 5G. I don't say this term define 5G, but these terms kind of come together with 5G. And the first one is this heterogeneous networks, which I kind of show one picture before that. The networks becomes more and more hybrid. And for the heterogeneous networks, there is kind of a clear definition for the cellular networks. We have macro base station ensure the coverage, and small cells provide capacity when and where needed. That's something like that. You have both macro cells and small cells. For this term, that brings like this frequency ranges. For the micro, typically we consider that lower band, carrier frequency 6G, the small cells 3 to 30G, and for the ultra dense case, that could be 30, 100G, and for the future, something beyond 5G, terahertz, and you can see this carrier frequency become more and more close to the optical frequency. Then the optical part could be also considered as a solution for the future cellular mobile networks. And the second term, many people talk about this usage scenarios. One talk about 5G, this enhanced. There are three major types. I guess you are clear with this. Very extremely one is this ultra reliable and low latency communication. People push the capacity at the same time, also push other performance metrics, reliability and latencies. And then we see many kind of crazy performance parameters, like 20 gigabit per second for the peak data rate, and average as 1 gigabit per second. The latency pushed to 1 millisecond, and also mobility that need to support 500 kilometers per hour. Many of those things, and I don't want to argue if that's needed or not needed, but that's more or less can trigger our thinking that when you think about if that's really a proper one, that's really needed. But the people also argue in this way that once you have network ready that can provide this performance, maybe trigger many new applications. But typically the world does not play in this way. They first comes with a requirement and then push the network in this way. But anyway, and when people talk about this latency, very famous example saying that we need low latency for automatic driving. But have you think about that? 1 millisecond, how long you drive? And you can simply calculate long drive with
20
one
centimeters or so.
less than 20 centimeters. If you
Something
drive
like
100 kilometers, 3 centimeters,
Yeah,
3
which is
centimeters
ridiculous.
per 1 millisecond. Which decision you made in 3 centimeters when you drive? Maybe not necessary, maybe needed. If you think about future automatic driving's kind of environment, if the speed comes to 500 kilometers per hour, then several 10 centimeters like this, which decision you made in this distance. So that's kind of a bit crazy. But anyway, if we think about this is just a radio segment, and for the end-to-end, you can a bit relax this, like 5 or 10 milliseconds. But still, that's like a stringent one for the whole 5G system. And the third term is this centralized radio access network. People think about to put this BBU baseband unit out of individual cell sites and centrally pooling BBU in the central office. In this way, you get like energy efficiency and also maybe cost efficiency for the cell part. And then for this, that's kind of push a very straightforward challenge on the transport segment. Yeah, how you connect the remote radio head and the baseband unit pool, baseband processing unit pool, and there is new kind of term defined for the transport segment called Fronthaul. Maybe you also know this Fronthaul. And as for the new 5G standardization, they also think some function splitting, that part of BBU could be distributed along the way towards the user end. Then some other terms like middle haul, X haul comes out for the transport segment. And all these terms that I list have definitely impact on the transport part as well. And for my talk today, I will list our research activities to address different kind of terms here. And starting from the first one, this heterogeneous networks. And here I give more kind of clear picture. This is this heterogeneous figures. We have the macro cell for coverage and small cell for the capacity upgrade. And the small cell, it's not a very clear definition. Yeah, no, it could have this BBU function or not. If this and the transport segment is kind of pointed here. Yeah, the conventional one, this backhaul link to core, towards core, and the new one, the small cell to the macro cell. If there is no BBU function here, this link, it can be referred to as a Fronthaul. If there are a part of BBU function, that could be middle haul. If the full BBU functions in a small cell, then that's still the backhaul case. And here is this architecture list this Fronthaul, middle haul, backhaul distribution in a more clear way. And Fronthaul is the closest part towards the user end. This RRU, remote radio unit, is without any BBU stuff. And when the Fronthaul terminated, it means that the BBU functions is located here. And the middle haul is something between the backhaul and the Fronthaul. This distributed unit and the centralized unit is kind of have the part of base station functions. And also here I list some parameters for different transport segments. And when we look at these three major types of transport segment, that will connect different network entities, and the connections will be pretty different. For the Fronthaul, so far only that's a point-to-point link. And for the middle haul, that could be point-to-point and point-to-multipoint. The backhaul, as you have more advanced signal processing functions, so that's kind of affordable for the more complicated topology like multi-point to multi-point. And also the distance. Distance for the front hall, of course, that's the shortest one, up to 10 kilometers. For the middle hall, that's basically the conventional access, wild access network range 20 to 40. And the back hall, that could be even longer. That's even can cover the metro part, 40 to 200 kilometers. The latency requirement for the front hall, that's now the most popular front hall protocol is CPRO, Common Public Radio Interface, where they have very stringent synchronization requirement. So the latency should be like in this level, 50 to 200 microsecond. And the bandwidth, here I list like 100 gigabit per plus. In my later slides, I will kind of verify why such high bandwidth need in this point-to-point link. And the bandwidth required for the middle hall and the back hall row, that's much higher than front hall, but you see that this is bandwidth for the whole system, point to multi-point. So for each link, not necessary to come to this level. But for the front hall, that's really high, 100 gigabit per second and beyond for one link. Even fiber has a kind of not that easy to provide such high bandwidth. And also multiplexing, more close to the user end, the multiplexing layer will be lower. So for the front hall, the multiplexing almost in the layer 0 or layer 1. And middle hall, that's up to layer 2, MAC layer. And the back hall, you have more flexibility to do almost everything there. And now let's come to kind of the first research activity that we have for the 5G transport networks, these heterogeneous networks. Yeah, that's really benefits of heterogeneous networks. Yeah, many research people tell us this heterogeneous deployment do have benefits in terms of spectrum and energy efficiency. And how about the cost, economic viability? As I work more on the transport segment, I have a big argument on this. When you have more small cells, actually transport part will be more complicated, and that will maybe not necessarily bring a lot of energy consumption, because if you use fiber, that's very low energy consumption. But that do bring different things, or different maybe the problems on the cost issue. We have worked on the techno-economic framework for a 5G transport segment. We try to complement the existing methodology for radio access network, because when people saying this heterogeneous, they believe for the radio part, you have a gain on the cost. But once this transport segment also involved, and a kind of, there are still clear gain there. And we try to understand the economic viability for the overall 5G mobile network deployment. And we have one paper published in the HIV Wireless Communications this year to show our methodology, and also some, in my opinion, very interesting results. Yeah. If you are interested, you can see more details from our paper. And we have techno-economic modules like this, including different parts. For the total cost of ownership, that we need input from cost module, business module, and network dimensioning module. Network dimensioning module also need input from the architecture, how the network architecture is, and topology, what kind of topology you use, and market module, what is the user penetration, what kind of service and quality of service will be provided for this network. And the total cost of ownership is not only the target for this work. Techno-economic is the final one, but techno-economic also includes thinking on the profit. You can think about it in this way, even in your daily life, something with a low cost, not necessary to bring the highest profit. And for the operators, profit sometimes is more important than the cost. So yeah, so if you want to understand the economic viabilities, profit sometimes is more important than the cost. But of course, if you don't know the cost, it's difficult to calculate the profit. And for these TCO models, we also include kind of, that's an overall thinking, CapEx, capital expenditures, and operational costs. And CapEx include two parts. One is infrastructure, and the other is equipment. And for the equipment, we also think about the purchasing cost and also installation cost. Installation cost is not minor. It's actually for the telecommunication projects, installation cost is quite a lot. And for the operational cost, we include fault management and a spectrum fiber leasing, energy cost, floor space, and also this maintenance cost. And for the profit thinking, basically profit is dependent on the cash flow, and this net present value is a kind of common performance metric for the profitability, and the net present value will be highly dependent on the cash flow at each year for during the operation, and also the total operation years, and also one is a discount rate that estimates the present value of future cash flow. This is quite complicated, but the simple idea is that $1 today will be quite different from $1 tomorrow. So we need to understand how much, how valuable for the dollar tomorrow. So then in this way to compare the net present value. And also for these transport networks, we consider the different scenarios, 6 in total that reflect the kind of technology point of view. Now for the transport segment, for the 5G, we believe the microwave and also the fiber will be a viable solution for that. So we consider both microwave technology as a backhaul and also the fiber as backhaul. Yeah, the main use case we consider for the backhaul. And also for the radio access network deployment, we consider both homogeneous one and also heterogeneous one. And one compare homogeneous one and heterogeneous one, we consider the same user penetration and the throughput coverage for the area. And for the fiber, if we use the fiber technology as a backhaul, there are also different business models. For some operators, they are big enough, they could own their own fiber infrastructure. And for some small one, they could lease the fiber infrastructure. So if you own the fiber infrastructure or you lease a fiber infrastructure, we also divide that in these two ways. And here I want to show some results. I don't want to go to the details of how to calculate this. The results are quite interesting in my view. This one shows cost, and this one shows MPV, which is which reflects the profit. And what you will find that this heterogeneous, is not necessarily better than homogeneous. This is what we found. And here the total cost, including the radio access part, wireless part, and also backhaul part, transport part. And the backhaul part here will even divide with CapEx and OpEx here. So you'll see difference. If you look at the radio part, it's clear that heterogeneous are always better than the homogeneous. But if you include this backhaul part, that brings different stories. And also the profit part. The one which has the lower cost, not necessarily have the higher profit. You can see these two cases. The heterogeneous lease, fiber lease case has the lowest cost, but not necessarily the highest profit. That's could be better understand when you see the cash flow for different scenarios. So you'll see that for the microwave case, as the microwave provided limited bandwidth, compared with a fiber. The capex part in the first year, that's super high, which makes the profit even comes to the deficit in the profit for the heterogeneous case. And for this case, which homogeneous leasing, yeah, for this case, which has the highest profit, yeah, it's clear that if in the year 0, actually the first investment, if we keep that low, you are good at the profit. And for the heterogeneous leasing case, it has the lowest total cost, but not the highest profit. Yeah, the major reason, if you compare with this case, that's because of the first very beginning, kind of the beginning investment, the segment for the transport segment kind of takes makes this heterogeneous different.
I just have a question. Does it assume that leasing is available to all the sites?
Yes. Yeah, because this is more for the comparison reasons. We assume for these areas, fiber and microwave are available, and the leasing is also available. Yeah, that will be extreme case because for some cases fiber is not available. For instance, cross river, that's difficult. But we just want to have a kind of common understanding on the technology part, and also leasing and infrastructure. And for the leasing case, actually, like in Sweden, it's quite popular. Sweden is a bit different from the USA. USA, you have very dense areas like New York that have a super high sharing rate. So that's somehow maybe affordable, have the different infrastructure owners. But Sweden is basic, sparsely. Even for Stockholm, this big city will only have 2 million people, and yes, so the infrastructure is owned by the community, and the operators lease this fiber infrastructure from the community. That makes this infrastructure somehow cheaper for the operator, and also more, I'd say, the utilization is higher, better kind of organization. So this is a kind of interesting story to bring to us. Of course, it does not. The result, we don't want to use this result to kill the heterogeneous networks, but more like to bring the thinking that once comes to the 5G, only think about the radio access part might not that enough. As once the radio part changed, the later part, the supporting part also have the changes, which will maybe make the whole pictures a bit different. So for instance, for this case, we consider like a middle city in Europe. So for that case, you do need to consider heterogeneous. It brings cost benefits or not in this way. Okay, this is for the heterogeneous part. And here I also introduce a second work second research activities which we very much focus on this kind of use case, a very extreme case for the ultra-reliable and low-latency communications. And this is like when people talk about 5G, there are many kind of fancy applications require extremely low end-to-end latency. Here at least 4. Here, autonomous vehicle, industrial automation, VR, AR, and remoted robotics and surgery. And particularly for these autonomous vehicles, that's not only low latency for that, and also user equipment has a high dynamic and also have a high mobilities. And if we further look at this, for the vehicle-to-vehicle communications, if we consider this mobility, the car will move, and the total end-to-end latency, if we want to access some service, have the cloud that in the edge of core network, the delays will experience in this way. So for the end-to-end delays, we need to think about the wireless part, that's the segment, and the transport part, and also the processing at this server. And for that case, if we don't do the optimization in any part, that will run kind of, for sure, larger than 20 milliseconds, which might not tolerable for this ultra low latency communications. And one way is that to simplify this transport part, to push this server computing resource towards the user end, close to the user end in this way, to reduce the end-to-end latency. And this way referred as edge computing or mobile edge computing or fog computing. Basically, there are no big difference. For me, no big difference called fog computing or edge computing, although that's kind of defined or identified by different entities. And as I also mentioned before, the computing and communication now cannot be like separated. For the infrastructure, we consider for the communication also have the computing resource carried out. And for the fog computing or for the mobile edge computing, the kind of the closest position that you could put the computing resource in the infrastructure side is a base station. It's kind of hard to push this computing like in the access point where there is no business band, baseband processing, because basically they don't support layer 2 or layer 3 statistic multiplexing. It's very difficult to work with that. And another possibility is to put this computing power in the user end. But that's another extreme case. It's also run a lot of another problems will bring. And here we mainly consider putting this computing infrastructure at the base station and think about this infrastructure with cellular networks with fog computing. And if we look at this, what will be the challenges for the transport segment in this way? Service migration. Service migration has been, because if we consider this automatic driving or even driving services, the user equipment has a high mobility that could move from the one base station to another one. And for the cellular network, that's handover problem. But once we also consider this fog computing, there is another problem, like this computing stuff also, or service also need to migrate it or not. Follow the trace of the user equipment. Service migration is proposed to address this issue. Handover is more for the telecommunication network, and service migration here is thinking about the service in the computing part. And there are like two advantages. As typically for the base station, you put the computing power, that's typically very limited. You need some coordination strategies to make the load balance for the computing side. And you cannot run all the resources in a single fork node. But on the other hand, that also brings some issues from the transport segment. Because for the handover, typically that's go with the wireless part. But for the service migration, from the one base station towards another base station, that's involved the transport segment. And there could be three important things to address. One is a good fog resource management in the way that you fully utilize the fog resource at each base station. In this way, that's a bit kind of shift load on this service migration. And the second is migration strategies. When and where you do the service migration. And the third one also, of course, that's once this kind of traffic, service migration traffic comes, what will be the impact on the resource allocation in transport segment? Yeah, as what I mentioned in the very beginning, the bandwidth or the capacity or the resource in the transport is not limited. It's not unlimited. You also need to do some resource allocation optimization there. And here I'd like to introduce our work on these migration strategies. We basically think three cases. The first two cases as a benchmark. For the third one is QoS, quality of service aware service migration, which the migration is triggered by the kind of performance matrix. For instance, if with a delay, our latency requirements cannot be satisfied, the service migration will be triggered. And the scheme one, that's considered that there is no service migration happening anymore. So the service will not be moved, follow the choice of the user equipment as always set in one base station. That's typically put a very big challenge on the transport segment because those connections always need to on, and that's also as many nodes will be involved, the high bandwidth is required. And the second case is service migration triggered by the handover, which means that once user equipment moved from one cell to another cell, the handover happens. But at the same time, the service, this user equipment associated will also be migrated toward following the trace of the user equipment. The advantage for this case is that the access latency could always be kept low. But on the other hand, as migration cannot be done by 1 second, of course it cannot be, 1 second is even too long for the migration, cannot be done very quickly. So if you have too frequent migration, that will also affect the latency, the reliability a lot. We do some performance evaluation for these three strategies. We have service migration algorithms implemented by Python code, and we use traffic generation module using this Sumer. I don't know if you are familiar with that. That's a simulation of urban mobility. And for this case, we consider Luxembourg scenarios and also some background traffic model, because typically this backhaul segment is like shared infrastructure that hosts both mobile traffic and fixed broadband access at the same time. And we have like a simple assumption here, have sufficient resource to accept a migrated service at each front node. And also we consider passive optimal network as a solution for the mobile backhaul. And for the traffic, that's also similar as telecommunication traffic that have the two peak hours in the daytime and also the after work. And here we can see some latency results. And the scheme one, the latency is highly dependent on the transmission capacity. With a higher capacity, the latency will not be an issue for the scheme one. But of course, you need to make sure that you have a strong transport segment that can always assign enough resource for the service migration. And for the scheme 2, that's largely impacted by the downtime of service migration. When do the service migration, the whole service migrated from one node to another node, there will be some time period the service cannot be connected. And if the this downtime is too long, definitely that affects the latency for the service running. And scheme 3, where we consider the quality of service, that can take advantage of scheme 1 and scheme 2. So one, we have low transmission capacity. This QoS aware scheme could run very similar as scheme 2, where you always have service migration triggered by the handovers. Once capacity is long enough, this scheme 2 does not show any advantages because the performance is limited by the downtime. But the scheme 1 has no service migration, no penalty on this. The latency could be much reduced. But scheme 3 have a very similar kind kind of performance when the transmission capacity is high. So that's take advantage of both schemes. And for the reliability, here we define the reliability as a probability that the end-to-end latency does not exceed a maximum allowable latency level. 5 milliseconds and 10 milliseconds are two kind of threshold we considered. And you will see that, yeah, basically that's a very similar trend as a latency result. Scheme 1, that's affected by the transmission capacity in transport segment. And scheme 2, that's largely impacted by the downtime. And scheme 3, that take advantages of both schemes. And this is the part that we address the ultra low latency communications for the particular focus on the service migration part. And then also we have the third research activities on the Fronthaul. It's a very unique transport segment that's kind of introduced by the 5G, by the FeRAN concept. Fronthaul, that's kind of standardized by using this CPRO protocol, and now evolved CPRO also standardized by the 3 GPP organizations, and that's the protocol used for transmit the digitalized analog signals between the remote radio head and the BBU pool. And one way putting the signal processing functions at the central unit, the system requires extremely high capacity due to the large number of quantization bits. Here I give an example for the 5G new radio channels. If we want to have 25 such channels, the Fronthaul link rate needs to be beyond 100 gigabit per second. That's the reason, if you remember the table that I showed in the previous slides, the Fronthaul, which is point-to-point, and the need bandwidth beyond 100. And radio over fiber, where the Photonics meets the radio, is a very attractive technique because that can offer both long transmission distance and high capacity, which allowing for this centralized radio signal processing. We have one paper recently accepted by the Techno-economic magazine to show our idea how to make this Terabit digital radio over fiber system, both from the architectural level and also technology level. And the idea is that instead of our conventional single-mode fiber, here we consider multi-core fiber, one fiber with several cores. Then you are able to have the parallel transmission, utilize a spatial division multiplexing. In this way, that largely increase data rate for that. And once you have these multi-core fibers, we could implement these self-homologous detections. Use one core to transmit the local oscillator signals and the other cores for the data transmission. And in this way, this LO could be shared by all the other cores data transmission and to achieve pretty simple detection implementation at the reception side. And of course, we are also thinking about compressed quantization. We are using the lossy and lossless coding schemes on top of these multi-core fibers to further improve the spectrum efficiency and also the capacity. So that's the idea that we reach the Terabit digital radio over fiber system. For this one, I've got to talk about some literature study. Once goes to the digital radio over fibers, that's the kind of the work in recent years. And here shows the distance for that. That's typically cover up to 20 kilometers. And here shows the highest CPRO equivalent rate. And you will see that like less terabit case. And with our recent work, kind of push this to towards the terabit. And for the quantum orders, that could also go for quite the extreme case here, 4,000 something, which might not be necessary in the current situation, but that's kind of show how good the transmission system can reach this quantum order. We have the proof of concept demonstration to run the whole setup, and we show this error vector magnitude performance for different cases. Differential coding and vector coding is kind of lossy coding, and also we try combination of this coding with a lossless coding. Lossless coding including Huffman coding and atomic coding. Yeah, I guess maybe you are familiar with that. And we clearly see that with the help of this coding, the performance, this EVM performance could be improved. One is with 1.4 quantization bit, and the other is 1.6 quantization bits. Which means with this 7 point something, this 4096 quantum based 5G NR radio signals can be delivered over this radio over multi-core fiber. And if we combine this vector coding and the lossless coding, you can see that the improvement from the lossless coding is quite limited, which also means that vector coding has less redundancy for the signals. So kind of this lossless coding does not help that much with the vector coding, but compared with the differential coding, vector coding can achieve much better performance in terms of this EVM. And the whole system demonstrates the rates vary from the 1.56 terabits to 5.21 terabits. The quantum order is from 4,000 something to the 4 quantum. And in this case, that's 460 5G NR channels, new radio channels can be supported. And in this case, 1,295 5G new radio channels can be supported. So that's kind of very powerful Fronthaul link that we demonstrated. And this is for the radio over fiber. And what will be the beyond 5G? And as I mentioned in the very beginning, for the ultra dense case, you will have this up to 100 gigahertz. And how about above that carrier frequency? Yeah, this part, more than 300 gigahertz to 1,000 gigahertz. 1,000 gigahertz means terahertz, not yet allocated. There are some kind of problem there because attenuation in the higher frequency is quite high. So that will be problems for the long distance case. But for some like a short range case, that is still possible. So terahertz may have possibility in those applications, like very local access and cyber physical systems, like in the factory, and also maybe, two buildings, just between two buildings, that's very close part for the backhaul. And here we list some kind of range for different applications. We believe there is some kind of room for the terahertz communications. And as terahertz is very close to the optical, at least compared with the conventional radio frequency. So they are possible to use Photonics device to enable terahertz communications. The advantage is that will no bandwidth limitation from the electronics device, and the tunability is very good by using the Photonics, and also that could become have the natural compatibility with the fiber transmission, and that also simplifies the radio frequency front end. and which you can see the state of the art, this terahertz work. Here, this number shows the carrier frequency, several hundred gigahertz, and this one showing the data rate, and this one showing the distance. So you can see this is our very recent work. We're using 408 gigahertz as a carrier frequency, reach around 100 gigabit per second. This is for data rate in the air, and the distance is around 10 meters. So that's possible for some kind of short distance applications. And we also run this in fiber. So this demonstration is show that the signals run 51 kilometer fiber plus 10.7 meter air is here, and reach the kind of performance bit error rate like this way. That can reach the FAC with a BER 2.7 with power of -2. But of course, this is using very heavy signal processing recovery to achieve this one. So yeah, if we think about the latency, that might be issue here. And this work is collaborate with DTU, RISE, and also the university from China, Jiajia University and Huazhong University. Okay, that's more or less all my research activities. Thank you very much for your time.
Thank you.